I'm excited to introduce today's speaker, Jesus Rodriguez, Business Development Manager for JWC's Monster Separation Systems. Jesus has 20 years of experience in the water and wastewater industry. The last 15 years, he has specialized in screening equipment and municipal headworks equipment. He has been involved in the design and redesign of channel and gem screens, as well as other equipment. Jesus is thrilled to share his experience on how design impacts headworks screening systems. So Jesus, I hand things off to you.
Wow, thank you, Stacy. That was an amazing introduction. Thank you so much. Now, I am also want to thank everybody that's on the line. Thank you for joining us today. My name is Jesus Rodriguez, and I am the Business Development Manager for all the Headworks products here at JWC, and I'll be your host this morning or afternoon, wherever you may be. So 50 minutes really isn't a long time. This presentation is going to really meant as an introduction to a lot of information that we're going to cover a wide range of topics related to headwork screening equipment, what you need to know about some of the different technologies and how to apply them to your particular situations, why we screen, what are some of the technologies, and we'll do a little bit of optimization at the end as well. Now I'm just going to take a brief pause right now, and Stacy has an exciting poll for us.
Great. So before Jesus got into the discussion, we wanted to find out what you're most interested in joining this webinar. So please select all the answers that apply. We want to know if you want most interested in learning about different types of screens, understanding what is best for your application, leveraging operational efficiencies, or problems related to poor screenings. So we'll give everyone a few seconds to enter your answers, and then we will share the results. Great, so I'm going to close off voting and share the results. So that's great. We have a high interest in learning about different types of screens and understanding what's best for your application. So you definitely are attending the right webinar. Jesus will be discussing a variety of bar screens and perforated plate screens, so you'll get a great overview of the different types of screens. And he will be discussing what screens are the best for each type of application. So you guys have attended the right webinar, and we're going to turn it back to Jesus to help you learn about these topics.
Thanks, Stacy. So first, I want to give you a couple of things to keep in mind as we go through the session. So these are just some insights that should help you put into perspective a lot of the things that we'll talk about, right? So when we talk about new water treatment plant projects or wastewater treatment plant rehab projects, the capital cost of headwork screening equipment is really only about 1 to 5% of the overall budget. So it's not a lot. But your headworks is going to produce between 25 and 50% of the overall treatment. And that does depend on the opening size and the process, but it's very important. And I also like to say that Headworks is a pay me now or pay me later proposition. And what I mean by that is we know we have to remove the trash from the waste stream, so we can either do it right up front with very effective Headworks, or we can spend the next 20 years or so chasing the trash through the system. And we don't want to do that. So when we talk about Headworks and wastewater screens, what do we mean? So a screen is a barrier with a defined opening, a fixed opening, and it's used to separate one thing from another. In our case, we're separating solids from liquids, the liquid stuff from the chunky stuff. So your Headworks is the first and probably most important step in the wastewater treatment process. So great care should be used when designing and selecting Headworks equipment. Now, historically speaking, we've come a long way. From the earliest days of modern wastewater treatment, screens were not in use, and treatment was basically settling, more settling, and maybe some disinfection. But really, what I want you to take away from this slide is that Headworks screens have been continuously evolving toward finer and finer openings. And we see even today the advent of bar screens with smaller than quarter-inch spacing. Now, the nature of the materials that are being screened are generally classified in two categories, and that's organic and inorganic solids. Organics are generally natural things, so stuff that can be broken down and is useful as food for microbes in the biological treatment process. Inorganics are materials that are generally man-made, and this is trash, right? So not useful things. So plastics, paper, pop can straws, flushable wipes, and all of these things must be removed from the waste stream for both clean water and clean biosolids. So why do we screen? Why is it important? There are three primary reasons for doing this, okay? So first, effective screening benefits every type of process. So no matter what the specific process might be, by maintaining operational efficiency and peak capacity, screening is going to be beneficial. Now, maybe the most obvious or visible advantage is protection of downstream equipment, pumps, MBRs, mixers, all types of rotating equipment. These are things that we can see, right? So we know, for example, when a pump is clogged and needs to be deragged. But definitely the most important advantage of all is that Headworks saves you money. So by reducing the overall treatment cost, as we'll see, and who doesn't like to save a little money, right? So effective Headworks screening directly impacts the bottom line. So by reducing the time spent maintaining ragged up equipment alone can justify any expense on new Headworks screens, for example. And that's not all. The effect of maintaining operational efficiency in aeration basins and digesters drives down the ultimate cost of treatment. And for sure, the cost of power is the single biggest line item involved with the operation of a wastewater treatment plant. So anything that increases motor efficiency and reduces power consumption is huge. So that's probably the most important reason of all. And you know, we think that everyone sees the value and the necessity of good, effective Headworks, but sometimes, you know, it's not always true. So an example is, for example, the practice of removing screens from projects that go over budget. This is typically considered a good value engineering practice, but in my opinion, it can be a little bit short-sighted. So lastly, there is an important secondary income stream from municipalities related to recycled biosolids. You know, we talk about cogeneration, pelletizing, land application, and other processes. So these uses require the final product, the dried sludge, to be very clean or it can't be utilized. So let's bear that important fact in mind as well. So let's take a look real quick at what can be the result of poor screening, especially when we talk about protecting downstream equipment. Here's an example of what we're talking about. And this one's pretty easy to understand. It's a particularly common one. We see clogged or ragged over pumps, and certainly the advent of the flushable wipes isn't helping this situation at all. And here we can see sitting on the deck rags that have been removed from an MBR chamber. So this is particularly bad news, as MBRs, you know, are very susceptible to damage from this type of trash. So this is a potentially very costly problem. Now that we've looked at why it's important to screen, let's discuss a few of the more common technologies that are available. So we'll be looking at bar screens today, fine screens, band screens, and drum screens. And it's important to note that there are many other types as well. So spiral screens, step screens, which are a variant of the bar screen. There are grab screens and trash racks for very large flows and flood control. There's in-channel drum screens and technologies, semi-basket types, element type screens, and even more. Just very quickly, though, I want to show you these two because I'll mention them through in a couple of spots in the presentation. I just want you to understand what I'm talking about, even though we're not going to discuss them in detail. So we've got on the left there, the spiral screw screen. And on the right-hand side, we see a grab screen, the Bosker type. Now, I'll mention these again, so this way you have a reference to what I'm talking about. So let's get started by taking a look then at the bar screen. Bar screens include the climbers with a single rake arm, what we know now as the multi-rake screens that have many rakes to continuously clean the bar rack, step screens, the grab screens that use the claws or buckets to clear large flows of heavy debris, and trash racks, just to name a few. But all of these share the vertical bars as the screening media, which is essentially a long slot, which is as deep as the water column. So this is considered screening in one dimension, and it's why the relative capture rate is low, because if, for example, you're a piece of paper or a straw, it's pretty easy for you to squeeze through that slotted opening. Now, they're also front loading and front cleaning, which means they have no possibility for carryover. Now, this is a good feature. So anything that gets captured on the face of the screen will be removed and not reintroduced into the waste stream. Multi-rakes aren't just for headworks anymore. They can be found in wet wells, pump stations, various industrial applications. They're utilized in septic receiving. And of course, these were the original core screens. So it's not uncommon to see them employed with 1 to 3 inch bar spacings for raw water intake. And of course, the very common 1/4 inch bar spacing, which is probably the most common equipment that we see in headworks today. Now, these are very versatile. They can be easily retrofit into existing channels and are relatively inexpensive in comparison to other in-channel options. And JWC provides them down to an 18-inch width, so they can be used in the smallest of plants. Now, you have to know what you're getting into with a multi-rake. So these machines have a relatively low capture rate efficiency in the 40s to 50%. Now, periodically throughout the presentation, I'm going to mention capture rate efficiency, and I want you to remember that when we quote these percentages, we're talking about everything that enters the headworks, right? Not just things that are larger than the bar spacing. So unless we are trying to use some advanced control strategies, for example, the bar screens can allow quite a bit of trash into a wastewater plant over time, and this can definitely become an issue for operators. Now, the second group of screens we'll discuss are perforated plate or mesh line screens. Again, there are various types, including the spiral screw screen, which we saw at the top, Throughflow fine screens, the band screens, internally fed drums, and others. This group of equipment makes up the bulk of what we consider fine or ultra-fine screens in the industry. And they're characterized by high to very high capture rate efficiencies because they employ the perforated or square openings, which allow them now to screen in 2 dimensions. So this is the reason, one of the reasons for their high capture rate, in contrast to the bar screens, which screen only in 1 dimension. So it might be useful to take a quick look at what we mean by that. Now, I told you the multi-rakes use one-dimensional screening, and that perforated screens employ 2-dimensional screening. So on the left-hand side, you can see the bar screen and why we say if you're a piece of paper or a straw, it might be easy for you to squeeze past the screen and become screening's bypass. On the right-hand side, it's easy to see now the difference when we're screening in 2 dimensions. It's much more difficult for large objects to bypass the screen, and that's the reason perforated type screens have such a high capture rate efficiency. And just so we're clear then on what we mean by bypass and as opposed to carryover. Bypass is trash that is captured by the screen, and then for some bypass is not captured by the screen. It just bypasses the screen altogether, right? So it circumvents the barrier somehow and enters the wastewater treatment plant. Carryover, on the other hand, is trash that is captured by the screen, but through some mechanical means isn't effectively removed from the screen and then is reintroduced to the wastewater treatment plant process. So going back to the perforated plate screens, specifically, let's look at the Throughflow or continuous belt perf screen. Now that's a mouthful. Because these can be installed in both existing or new rectangular channels, we consider them also to be quite versatile. As well, they are routinely employed in a multitude of applications, not only Headworks. So as we said, they have high capture rates compared to other in-channel technologies, and they're moderately priced. So these 2 factors really make the Throughflow fine screen the best value proposition for the performance and the cost of ownership that they have. So in addition to that versatility, let's take a look at other features that are advantageous for this equipment. So the screens can employ stainless steel or UHMW screening panels. They're very easy to install, and the maintenance that's required is very manageable. Now, these are also front-loading screens, meaning that they collect trash on the face of the screen, but they're rear discharging. So the possibility of carryover does exist with this type of equipment. Now, as we saw a moment ago, anything that is captured on the screen and transported over the top of the discharge point that is not effectively cleaned off the panels by the water spray, or this equipment uses a rotating brush as well, does have the potential then to be introduced into the waste stream and enter the treatment plant, thus becoming screening's carryover. So for that reason, this equipment is not recommended for use in front of membranes, right? Any screen with the possibility for carryover are not recommended for use in front of membranes because, of course, the membranes are very sensitive to damage by any of that trash. The cleaning method here uses both the water spray and a rotating brush. The brush is highly important. While the majority of the panel cleaning is done by the spray wash water, the brush is necessary to accomplish that final 5 to 10% of cleaning. So for that reason, the brush is considered a maintenance item, and it has to be carefully maintained and adjusted over time. Cleaning and maintaining that brush isn't the most enjoyable job in a wastewater treatment plant. So for that reason, there are many owners don't favor this equipment because of the brush. They would prefer something that doesn't have the brush that needs to be maintained. Now, fortunately, there is an alternative. The brushless fine screen. JWC is providing a brushless version of the fine screen. But Jesus, how is it that your screen doesn't require a brush, you ask? So the brushless screen has a very specific application. Obviously, there are owners who really don't want the brush at any cost. So this is our target clients here. However, because the brush is removed, we add a secondary spray system to take its place, and water consumption is higher, and that can be an important consideration, obviously. Now, this variety is only available with UHMW panels. stainless steel are not an option. We found that the UHMW panels behave better without the brush compared to stainless. So this is pretty exciting, and we do have several installations already operating with success around the country. And these are just a couple of installation photos I wanted to show you about, the open area. So on the top right-hand side, we're looking straight through the screen, and we can see how that open area really allows this equipment to flow quite a bit of flow through. And you see full covers there in the middle, for example, that we provide for cleanliness and odor control. Now, the next screen in this category, we'll see the band screen. And band screens are employed primarily as Headworks screens and in front of MBRs. So along with the internally fed drum that we'll see next, the band screen is the preferred system for MBR pretreatment. Now, the reason is the inside-out flow pattern that the band screen employs. This keeps the dirty inflow always separated from the cleaned effluent. So the flow stream enters the throat of the machine, as we see here, and exits through the panels on either side as it proceeds into the plant. So for this reason, the dirty side and the clean side of the panels never meet. There is no possibility of carryover. And very high capture rate efficiencies, greater than 85%, are achievable, and that's always dependent on the opening side. Now on the cost spectrum, this is relatively the most expensive of the three technologies we've seen so far, but it has many advantages too. So in addition to the high capture rates, the band screen has individually replaceable screen panels. And because it's installed with the panels parallel to the incoming flow, the panel lengths are not limited by the width of the channel. Now, this is really important since it offers us an opportunity to introduce more flow into any particular channel than, say, a Throughflow fine screen would have, since the Throughflow screen is, the panel lengths are limited by the channel width. So when a client's trying to get the max performance from an existing channel, the band screen lets us push the envelope, in that direction. So this diagram illustrates what I mean. So we see the dark red lines show how the screen is installed in the channels, and the blue arrows show the direction of the flow. So we see how it enters through the front of the screen and it exits the sides before proceeding into the plant. And you can see on the back side of the machine, it's possible for us to introduce back panels as overflow weirs or doors to allow us to bypass the screen if that becomes necessary. And then again, it illustrates the point I made before. Since you can see that the screen is installed with parallel to the flow, we can make those panels almost as long as we want. And that's how we introduce more open area and get that additional flow if we're looking for it. So to recap, the band screen has very high capture rate. We can use 1 to 6 millimeter openings on the stainless or UHMW panels without the possibility for carryover. So this equipment does need relatively more maintenance than the Throughflow or the band screen, because this screen does have a lot of sealing area that has to be maintained periodically. So here I wanted to show you on the bottom left-hand side how the solids are removed from the screen. So as they're collected on the inside of the band, they're deposited in the sluiceway or a conveyor that is directly attached to the screen. So the last bit of equipment that we're going to see today is the internally fed drum screen. Honestly, the most versatile of all the machines we're going to see. But since it's not installed in rectangular channels and generally requires pumped flow, it's not nearly as popular in wastewater treatment plants. But they really have a wide range of application. we'll see them in Headworks, in front of MBRs, at sludge screens. They're very popular in septage receiving, and a really wide array of industrial applications as well. So the reason we don't see these more in Headworks is because they generally require pumped flow, although gravity feed is possible as well. But as I said, they can handle a wide range of flows, up to 13 mgd in a single unit. So that means that they can get quite large, up to 72 inches in diameter, up to 250-inch long drums. And they're routinely installed outside in warm weather climates. But typically in cold weather climates, they've got to be indoors. So for very large installations, this can make the capital cost unattractive. So there's definitely a break-even point relative to cost at this point between the drums and then in-channel installation. But they have great benefits. Very, very high capture rates are possible, and this is because the lack of sealing surfaces, right? There are no physical seals in the internal drum screen. So for that reason, along with the band screen, they're very desirable in front of MBRs. Now, interestingly, there are designers who prefer drums and some who prefer band screens. So it seems for them a matter of philosophy. Now, all mechanical equipment, including screens, can fail, and various designs fail in different ways. So when a band screen fails, it's usually in a sealing issue. So some trash will start bypassing the screen through a damaged seal, and that's going to directly foul the membrane. But when a drum screen fails, it's not a sealing issue. It's because that the screen has become overwhelmed, and it tends to spill out onto the deck unless there's a bypass. So you get an overflow, and that's not good either, right? So nobody wants to see the inflow out on the ground. So typically we make sure that they're well protected in case of an overflow. However, in that case, there's no chance for the membranes to be fouled. So, which do we prefer? Do we prefer the membranes to possibly be fouled, or do we prefer to possibly have liquid on the ground? So it's one way, 6 in one hand, half a dozen in the other. But as I indicated, drum screens are very versatile. Using different medias, they're employed in many, many areas. And about 50% of the units that JWC provides are in the industrial screening sector. So on the top right shows fish offal, and we see veggies here, and I think chicken feathers. And on the right is the chicken offal too. So let's illustrate the flow pattern through a drum screen, okay? So the flow enters from the left-hand side. It's either pumped or fed by gravity, and goes into the distribution box, and then it flows out over either side or a single side out onto the drum where the solids are separated, and the screened effluent flows out through the bottom, as these screened solids then are augured out from left to right until they exit the drum on the far side. So it's very simple and effective. And here we can see the indoor installations that we mentioned earlier. So that's going to be it for the 4 technologies that we're going to cover. So let's look at some design and application considerations, right? So today we've been mainly concerned with Headworks, but each of the categories that we looked at, I illustrated that they all have multiple uses, and this diagram shows where those applications are. So starting from the collection system, where we see the screens in pump stations, we've got septage receiving, digester cleaning, which is a really interesting emerging application where The idea is we want to recirculate that digester continuously to keep the efficiency high and keep the trash out so that they don't have to be cleaned very often. We touched a little bit on the sludge cleaning, and we mentioned the biosolids applications and MBR pretreatment. And even in the post-treatment process, you can see a screen. So oftentimes in industrial sites, there could be some bit of unwanted material that is just impossible to remove through the manufacturing process, and we'll have to attack it and try to remove it, right at the end of the system. So I've given you a lot of information on the benefits of all the technologies that we've covered. And when trying to consider which type of equipment is right for you, you have to know, what is most important to you. So is high capture rate efficiency most important? Then we might, we're going to consider drum screens or band screens and even the fine screens. If you're considering large flow applications, then we'll see the grab screens or trash racks, or the fine screens and the band screens. Again, we know we can get quite a bit of flows through that equipment as well. If the budget is most important, then we're going to consider spiral screens or multi-rakes. And if limited footprint is the key, then probably a vertical screw screen is going to be important to you. But these are not the only design considerations that are going to be considered. We're going to need to look at some other things that are going to help us to select the right equipment for us. So particularly for in-channel applications, what are the most critical design considerations? Okay, so screening media. What are the size of the particles that I'm trying to screen out? What systems are downstream that I need to protect? There are hydraulic considerations. What does my hydraulic profile look like? Or do I have any upstream or downstream limitations? Is capture rate efficiency important? What kind of controls are needed? Do I want to implement any advanced control strategies? And probably the most basic requirements are budget, footprint, and volume, peak flow rate. So these are probably the bare minimum or most important considerations that we have to keep in mind. So really quickly, we're going to take another brief pause right here, and Stacy has a poll question for us.
Thanks, Jesus. So obviously Jesus has started the discussion on design considerations, but before he goes a deep dive into that, we are curious to know what is the most important consideration when you are doing your screen design. So please select what you consider the most important between peak flow, head loss, capture rate efficiency, budget, or footprint. We'll give everyone a few seconds to enter their votes, and then we will share the results. And then while everyone's entering their answers, I do want to mention that we will be taking questions at the end of the webinar. So if you do have questions, please enter your questions in the GoToWebinar questions bar, and we will do our best to answer your questions, but please enter those questions so we have them. So in looking at the results, wow, capture rate efficiency is definitely what is the most important design consideration when you guys are specifying your screen. So hopefully Jesus will give you all the right information to help you specify for capture rate efficiency. So Jesus, back to you.
Thanks, Stacy. That's awesome. So capture rate efficiency is definitely one of the absolute most important considerations, and over time has become more and more important. So we will discuss that in a minute. So once we have those three basic considerations of budget, footprint, and maximum flow, we can address the other design considerations, right? So starting with the media. Now, in-channel screens will use the perforated plate or vertical bars, And generally, wedge wire and mesh are seen in drum screens, although it is possible to see band screens with wire mesh. And we only mentioned wedge wire on a multi-rake in passing earlier. But opening size then is directly correlated to capture rate. So, right, as the opening gets smaller, the capture rate efficiency goes up. But so does the head loss of the equipment. And obviously, the process will be the main driver on the opening side. But there's a delicate balance then between hydraulic capacity, opening size, head loss, and capture rate and flow. All of these factors are intertwined. One directly affects the other. So of note here then is because we limit the flow as we go down in opening size, sometimes it's not possible to say implement a 3mm opening because we just don't have the hydraulic capacity. But by using some smart operational strategy, we can actually get as good or better performance from a larger opening, and we'll see in just a few minutes how that can be achieved. So what is head loss as it relates to a screen? It's simple. It's the difference between the water level upstream of the screen and the water level downstream of the screen. That's it, right? So our consulting engineering partners will have developed a hydraulic profile for the entire wastewater treatment plant, and they can usually tell us the value of the water level downstream of the screen pretty accurately. And what we do as suppliers then, we want to help determine what are the appropriate channel dimensions and equipment selections for that particular design. So these decisions will be made according to whatever restrictions may exist. For example, if there is a strict upstream elevation limit, a common example is a limitation that might exist in a collection system where we know there's a maximum upstream level that may surcharge a sewer or flood Mrs. Johnson's basement. And these situations, need to be avoided at all costs. So here is an example, a simple hydraulic profile. This is something that's very important to us as equipment suppliers. Then on the far left-hand side there, we see right at the head of the plant a depiction of the headworks, and we'll see the water levels in front and behind that diagonal line that represents the screen. So that's the downstream and upstream levels that the designer has targeted, and we're going to try to meet. Now, just want to say really briefly about head loss, because it has become very common to see maximum head loss figures quoted in project specifications today. But I really want us to think about what is more important, the head loss of the equipment or the upstream elevation. Because I'm telling you that the equipment today really is designed to withstand head loss differentials often 20 times greater than the actual head loss that we'll see in operation. So limiting the head loss in a spec isn't necessary most often. Instead, it's my opinion that we should concentrate our design efforts on the upstream water elevation. Ultimately, I think that's what matters the most, that we keep the flow streams inside the channels that we're designing and adequately take care of any upstream limitations, not flooding Mrs. Johnson's basement, for example. Now, that being said, head loss figures will vary from one supplier to another, but all things being equal, and that's important, head loss is probably going to be within 10% of each other between one piece of equipment from supplier to supplier. That 10% difference in head loss is reasonably attributed to the design differences. However, if you're working with various manufacturers and one's demonstrating a head loss figure that's 30 or 50% less than all the others, it should give you pause to ask more questions, because sometimes what seems too good to be true actually is. Now, when it comes to controls, the sky's the limit, right? And it has been the trend over the last 15 years or so, especially to see more and more elaborate control systems being specified. Now that's understandable, as real plant SCADA systems have become very commonplace, and the desire to collect and utilize data increases. So while this is great, it's not always necessary for every application. You know, the PLCs and our standard panels that we use to operate multi-rig screens, for instance, are thousands of times more powerful than the computers that were used to send astronauts to the moon. And we're not going to the moon, right? So when it comes to controls, if possible, I like to use the KISS philosophy and keep it simple. Having said that, we arrive at the time where I'm going to show you how it's possible to get the same or better performance from a 6mm screen that you might expect from a 3mm screen. And you're saying, hey, Zeus, that sounds crazy. What sorcery is this? I said, no, but it's really simple if we just have to understand three things, okay? So first, it's important that no matter the design or the supplier, a screen has its highest capture rate efficiency when it's stopped, and its lowest capture rate efficiency when it's running. So a screen has its maximum capture rate efficiency when it's stopped, and the lowest capture rate efficiency when it's running. So imagine what happens when a screen fails and it stops running. What happens? It becomes completely matted over, and it gets so full of stuff that nothing gets past it, not even water, right? So that's 100% capture rate efficiency. Awesome. Well, that's not so great, you know, in a Headworks, because our inflow is going to overtop the channels, and we don't want that. So we know we have to run the screens, but what we want to do is run them only as much as required and as slowly as we can to maintain that upstream water level below any restrictions that we've set for ourselves. Now we can do this using VFDs, for example, and start the screens as slowly as we can and run them as slowly as we can for only as long as we have to. So of course, as the flows increase eventually to the peak, we will end up in a situation where we're forced to run the screens at full speed for extended periods. But when we can, we will utilize that optimization strategy. Now, as an example, I was involved in a greenfield project with oxidation ditches, and they had a ton of prop-driven mixers. And they also had brand new 6mm Throughflow fine screens. When the plant started up, they found that they were deragging one of these mixers every week. Obviously, it was not the expectation that they were going to be deragging mixers that often. So eventually, I was called to come down and take a look. The ragging was really bad, with these yards of what we call witch's hair, or very complex rag balls, that obviously didn't get past the screens that way. So we sat behind the screens and observed what was passing through the screens, and it seemed like for hours, and we couldn't see anything. So finally, we installed with essentially household window screens behind the fine screens to find out what it was that was passing through the screens. And what it turned out to be was this very fine fibrous material and human hair and a few mop strings here and there. And this was all recombining inside the plant to form those massive rag balls and witch's hair. So the solution turned out to be installing the VFDs and running the screens the way I described before. So very slowly and as little as possible. And this way we were able to shear those fibers out of the waste stream. And we did, I expected that the mixers, if they were deragging one a week, that maybe they'd start to derag one a month. And that would have been a relative success, but the ragging stopped altogether. So I know it works, right? So it looks like we're gonna take one more quick pause right here. Stacy has the last poll for us.
Thanks, Jesus. I just as a reminder, we will be answering questions at the end of the webinar. So please enter your questions in the questions field in the GoToWebinar toolbar so that we can answer your questions at the end. So the last polling question is, we do want to make sure that you've gotten all the information that you need to specify your screens. If you would like to be contacted by one of our experts to discuss screening solutions in more details or for your particular environment, please select anything that applies. If you want to know more about bar screens or drum screens or fine screens or any other questions about screens, please select those fields. If there's no additional information you need, there's the not at this time answer. So we will let a few more seconds to let everyone enter their answers, and then I will turn it back to Jesus to finish off the webinar. Jesus, I'll turn it back to you.
All right, thank you, Stacy. So with just the time we have remaining, just a couple of things on maintenance strategies. Okay, so there are three predominant maintenance strategies that can be implemented, and most plants or most localities are somewhere along the continuum of all three, right? So they use a combination of all three from time to time. So the first is run to fail. And this is exactly what it sounds like, okay? So no real maintenance is performed and the equipment is allowed to run until it experiences a failure. Now this is, it sounds terrible, but it's actually appropriate in some cases. So for example, sealed units or electrical components, there's no maintenance that's ever required, but they will eventually fail. And when they fail, of course, it's a surprise. And it's really inconvenient and can never be planned for. So this is not a good strategy for your Headworks screening equipment. The most common and appropriate strategy is preventative maintenance. It's what's recommended for screening equipment, and that's where we see routine maintenance is performed on the equipment on a regularly scheduled basis. Now, this is intended to keep the equipment running and lessen the likelihood of unexpected failures. Now, while this strategy does maintain the general health of the equipment and achieves its intended lifespan, when failures do eventually occur, they're still unexpected, right? So getting rid of that unexpectedness is what we're trying to do then finally with the predictive maintenance strategy. So here we try to predict how and when a piece of equipment is going to fail so that repairs can be made prior to the actual failure, thereby preventing it altogether. So this is done through the religious collection and analysis of data. And there are many different types of data that we can collect, from vibration, noise, amp draws. We can use different imaging technologies, the thermal imaging, for example, infrared, to collect those data points, right? So on a screen, for example, if we could continuously monitor flows and head loss, that could help us understand when a screen is becoming permanently blinded, right? So when the cleaning system isn't working optimally. So understanding that could be important for us when we need to maintain that screening media. Another interesting one related to noise collection is the cleaning brush on a fine screen, for example, makes a really distinct noise when it's properly engaged with the panels and working properly, okay? So more than once I've been called out to plants that were complaining that their fine screen wasn't operating or capturing the same amount of stuff that it used to. And what we found was that when we went up to the Headworks, we hear silence, right? Silence as the screen is running because that brush is no longer even in contact with the panels and hadn't been adjusted, right? So So we can adjust the brush at that time, and if we know what that sounds like, we can always understand when that brush needs to be maintained. So collecting that data allows us to stay, really on top of things. But good maintenance, like good screening, definitely drives down cost, but it does obey the law of diminishing returns. So we don't want to be spending so much time and money collecting data that we can no longer use, or that's no longer giving us any benefit. We want to find that sweet spot where our equipment is running at peak efficiency and we're spending just the right amount of time and money doing it. So that brings us to the end of our show, but I've got one last thing that I want to share with you. And I can tell you that as a capital equipment manufacturer, with great certainty that you've been right about one thing for a long time. All of you have wondered this, and I'm going to tell you it's true. Rotating equipment is carefully designed to fail only late at night and on weekends when you are not there, right? It's a gift. It's something that we provide you free of charge. Now, by telling you, I'm going to give you help, though. I want to help you. So I'm going to tell you when to expect that next surprise mechanical failure, and it's in the form of a question. So please go ahead and type your answers in really quickly in the questions bar. Again, here we go. Who knows when the national peak flow occurs at our wastewater treatment plant? At what moment does the national peak flow occur at our wastewater treatment plant? I don't know if Stacy can see some of the answers that are coming through. And hey, and if you want to make a joke, this is a good time. I love a good joke.
So believe it or not, people are coming up with the right answer. Go ahead and show it, Jesus. We have a smart audience.
All right, so y'all know that's correct. So at the halftime of the Super Bowl is when the national peak flow occurs, and you can imagine all those toilets flushing at the same time. So now you know when to expect that next surprise pump failure, and you can thank me for it. So with that, thank you for your attention. You've been a great audience, and we'll take questions.
Great. Thanks a lot, Jesus. Just a few quick housekeeping items before we get to questions. As I mentioned before, we will be making a recording available of today's webinar. It will be available on jwce.com, as well as you will be receiving an email of how to access the recording. For those of you who need a certificate of completion for credit, we will be sending out information via email over the next 1 to 2 business days for information on how to download that certificate. Also, I know some of you have asked about the Muffy mask for the first 50 registrants who attended today's webinar. Again, we will be sending out an email to you for mailing address for you to receive your Muffy mask. And finally, we really do appreciate the time you've taken to join us today to learn about how design impacts Headworks screening systems. We have been overwhelmed with a lot of excellent questions, and we're happy to stay on for a few extra minutes if necessary to answer your questions. But if for some reason we don't answer your questions, we will be reaching out to you via email over the next few days. So with that, Jesus, for the first question, someone has asked, when you receive septage and you just want to use a multi-rake screen when you don't need a real high SCR for the process, what things should the designer be keeping in mind?
That's a good question. So you can definitely use multi-rake screens in septage receiving. Really, the thing with septage is to keep it moving, right? So yeah, want to be able to keep it moving. So adjusting the rise and run in an incoming channel in front of a multi-rake is going to be important. And you can add water. Okay, so you can add water in the septage process to keep it moving, and it really helps to do so. So those are probably two things that I would suggest in front of using a multi-rake. Is don't be afraid to add water in front of it to keep keep it moving and make sure that all your solids get into the multi-rake.
Great. Next question, Jesus, is what are your thoughts on putting screens at pump stations? And a part two is what are the reasons for handling screenings at a pump station rather than passing them on to a treatment facility?
That's another excellent question. So, that's one of the main concerns uh, with screening at pump stations is they're oftentimes remote or unmanned, and you have an issue now. It says, all right, if I screen here because we're having a problem at this station with either with the pumps or with a heavy inflow of solids. If I screen here, now now I have to deal with the solids, everything that I'm taking out, and that can sometimes be a challenge. So that's probably the main consideration. So honestly, if at remote pump stations, it's probably not really useful to screen for that reason. And at those very remote stations is where grinders can be very useful, so that we can protect the pumps so they don't get clogged, and we pass those solids on down the system until they reach the headworks. But then we know if we're doing a lot of grinding in a collection system, we know that we're going to need real fine screening at the headworks eventually.
Great. Thanks, Jesus. Next question is, it's a two-parter. Why do screens work better when stopped or moving slowly? And do all screens work better under these conditions?
I'm sorry, Stacy, can you repeat the question?
Sure. The question is, why do screens work better when stopped or moving slowly? And do all types of screens work better under these conditions?
So excellent. So as I tried to explain in the example, all types of mechanical screens, even drum screens, have their highest capture rate efficiency when they're stopped. Okay, so if a screen is not moving, it will eventually become completely clogged with solids and have 100% capture rate efficiency. Nothing will be able to pass it, not even water. But obviously, we can't operate our system that way. We've got to let the screens move. So what we're trying to do is we're trying to strike that perfect balance and keeping the capture rate efficiency as high as possible by only moving the screen or operating the screen when it's absolutely necessary. So operating it as slowly as possible for only the time that it needs to be operated. And the answer is yes, that all screens behave in this way.
Great. The next question is, how do you handle outdoor screening operations in cold weather environments? And is heat tracing effective?
So heat tracing can be very effective. There are thousands of outdoor installations in cold weather sites that utilize heat trace uh, with varying degrees of success, I will admit. Okay, so I've seen some, what I call poopsicles, right? So on a rear discharging screen, for example, if that discharge starts to get frozen before it hits the dumpster, it can be an amazing sight, and it's terrible. So heat trace is something that it's more of an art form, right? And then depending on the type of screen, it's important to know where a particular design needs to be heat traced. Okay, uh, and sometimes it can be very useful if the inflow is kept warm. So enclosing the channels to keep that gas and all of that stuff as warm as possible, that helps. Sometimes that will reduce the amount of heat trace that can be necessary. So yes, it's effective, but sometimes it's a trial and error process. So if you're using heat trace today and it's not exactly working out exactly the way you wanted, we can look at the design and we can make suggestions on how to improve it.
Great. Someone had a question about using screens for digester cleaning, and is it a good idea? You want to elaborate on digester cleaning using screens?
Sure. Um, so today we have a few clients that are using internally fed rotating drum screens for digester clean out. Now they fluidize the digester and they drain it down as much as they can. And as they're draining it, they're pumping that digester fluid through the drum screen to clean it while they're cleaning the digester. Obviously, that screened pumpage, that screened effluent that's coming out of the digester, then they send it to the headworks because it's got to go somewhere. So they send it to the headworks because it's already been screened out, and then they continue their process and they're removing solids until the digester is fully cleaned out. Now, the idea eventually is that this process will be a continuous process. Right now, that digester cleaning using the drum screens is still done on every 2 or 3 or 4 years. But once you do it the first time, the second time gets easier, and the third time's easier still because you're trying to keep those solids out of there. And eventually, what we hope to be able to do is to make it a continuous process where we're continuously circulating the digester and keeping it clean all the time. So we never have, so that eventually we hope that we'll never have to take another digester down for cleaning.
Great. So we're just a little past the 10 o'clock hour. I'm going to ask our last question. If we did not get to answering your question, we will respond via email. But again, thank you everyone for joining us. So the last question, Jesus, is can high pressure wash water required by a fine screen system be supplied by processed water instead of municipal potable water?
Absolutely. The answer is yes, and in 95% of the cases that's the case. So we just have to understand what's the nature of the MPO, and we'll always tend to provide additional screening for that water. So we'll provide screens for the incoming wash water, and that's typically like a Y strainer type, maybe with 80 mesh or 70 mesh, so that we don't clog the nozzles in the cleaning system. But yes, absolutely, we can use processed water.
Great. Jesus, thank you so much for your time and excellent presentation. And thank you for our audience for joining us today for learning about Headworks screening and design considerations. Again, a recording of this presentation will be available in the next few days, so be on the lookout for how to download that webinar recording. Thank you again and have a wonderful day.